We're now going to look at problems involving the colligative properties, freezing point depression and boiling point elevation. For freezing point depression, our equation looks like this. Delta TF equals KF times M. The delta T means the change in temperature of the freezing point. KF is a constant, and so I will give you the value for KF, and M is the molality. Similarly, with boiling point elevation, our equation is delta TB equals KB times M, where delta T is the change in temperature, K is that constant, and M is molality. So let's look at some problems with these colligative properties. Anytime you want to calculate freezing point depression or boiling point elevation, you have to find the molality first. So in this example, I want to find the molality of a solution. It's a benzene solution, so benzene is my solvent. I have 400 grams of solvent, and I have 200 grams of acetone as my solute. In order to find molality, I'm going to take the 200 grams of the solute. It needs to be in moles, so I need the molar mass of acetone, which is 58. And then we're going to divide by kilograms of solvent. 400 grams would be 0.4 kilograms. So my molality, my concentration for this solution is 8.62 molal. Once I know the molality, I want to calculate delta TF, which is KF times M. So delta TF would be equal to KF, which I'm given as 5.12 degrees Celsius per molal. And then my molality, 8.62. And so the change in the freezing point, delta TF, is equal to 44.2 degrees Celsius. So my freezing point will decrease by 44.2 degrees. Let's look at the next problem. What is the freezing point? Not the freezing point depression. What is the freezing point of a solution? 10 grams of glucose, 50 grams of water. So I'm going to find the molality first. Glucose is my solute, so I've got 10 grams. Need the molar mass of glucose because I need moles. Molar mass of glucose is 180 divided by the kilograms of water. 50 grams would be 0.05 kilograms. So my molality, when I divide, 1.11. I want the freezing point, so I need to do delta TF equals KF times M. KF for water, I'm given in the problem, 1.86. My molality, 1.11, I just found. And so the change in the freezing point, when I multiply these through, 2.07 degrees Celsius. I want the actual freezing point. Well, freezing point gets lowered. It's going to get lowered by 2.07 degrees Celsius. Water normally freezes at 0, so it's as simple as taking 0 minus the change. And so my new freezing point of the solution, negative 2.07 degrees Celsius. All right, let's look at a boiling point problem. Just like with freezing point, I need to find molality first. So I've got a solution of calcium chloride in water. So molality would be 1.25 moles. I'm already in moles. Divided by kilograms of water, which would be 1.4. So my molality comes out to 0.893. Okay, this problem is a little different in that this solute is ionic. It's got a metal in it. So instead of producing just one particle in solution, this actually produces a total of 3 because when you put calcium chloride in water, it separates into Ca plus 2 and then 2 Cl minuses. So 3 particles in solution, because it's ionic, we're going to multiply my molality by 3 because there are 3 particles. So my new concentration, 2.68 molal. When I get to my delta T problem, which is delta TB equals KB, because we're in boiling point, times M. KB, we're given 0.512. And molality, we're going to use the 2.68. So if it's ionic, if it has a metal, make sure you multiply by the number of particles. So delta T for this is 1.37 degrees Celsius. And then if I want to find the boiling point, well, the normal boiling point for water is 100. Boiling point gets elevated, so plus the 1.37. So my new boiling point of the solution, 101.37 degrees Celsius. Freezing point gets lowered, boiling point gets elevated. This last problem I'm actually going to skip because we are not going to work backwards. This is a problem where you work backwards to get the mass. So we're actually going to skip this problem and kind of go off the previous 3 examples.